Hello everyone, welcome to the Shimatsu-sponsored ASMS webinar. I'm Kevin McLaughlin at Shimatsu Scientific Instruments in Columbia, Maryland. I'll be your moderator for today's webinar, Shimadzu Reboots LCMS triple quadrupole technologies and capabilities at ASMS 2020. Before we start, I have a couple of notes for everyone's viewing. The webinar console has a variety of items to help enhance your experience and interaction with us. In the screen, you'll see the following items. On the left are survey questions that you may fill out anytime during or after the presentation. In the center is the area for presentation slides. Just below the slides are the resources. In here, you'll find links to web pages and posters relevant to the topic. On the top right-hand side is the widget for questions and answers. Please submit your questions during the presentation through this widget. We will try to answer them during the Q&A session. If time runs out, we will respond to your questions via email. Finally, along the bottom are the icons to bring up all these widgets in case they are minimized or hidden. Again, if you are just joining us, I'm Kevin McLaughlin, your moderator. Today's discussion will focus on Shimatsu's new triple quad LCMS technologies and capabilities. We ask that you submit questions through the widget, and we will answer all questions either during the Q&A session or via email after the event. It's now my pleasure to introduce today's speaker, Christopher Gillis. Christopher is the LCMS product manager for Shimatsu Scientific Instruments, the U.S. subsidiary of Shimatsu Corporation. He has spent the past 23 years with Shimatsu providing technical customer and sales support, specializing in LC, LCMS quadrupole, and LCMS TOF technology. Okay, Chris, take it away.
Thank you, Kevin, for that introduction. Welcome, everyone. We thank you for attending this webinar and for visiting Shimadzu at ASMS 2020. This year at ASMS, Shimadzu launched a new triple quadrupole mass spectrometer. Today, we're going to take a look at some of the important features that distinguish this LCMS from other mass spectrometers. In 2009, Shimadzu released our first triple quad. Rapid development of the product has taken place over the past 10 years. Sensitivity has been improved dramatically, and we now have a product lineup of 5 triple quad mass spectrometers. Today, we'll be discussing the LCMS 8060NX. This slide shows a cutaway view of the LCMS 8060NX. On the left-hand side, we see the ion source. ESI is the most commonly used ion source in LCMS. And proceeding from there, we see the inlet or the desolvation line, and then the ion optics. We have 3 ion optic components, the Q array and 2 multipoles. These are used to focus the ion beam. Then we have Q1, used to select the precursor, the collision cell, used for fragmentation, Q3, which is used for selection of the product ion. Then we have a electron multiplier and a pulse counting detector. 3 key areas of hardware development are going to be highlighted in this presentation, plus an additional area regarding parameter optimization. We'll take a look at the ion focus ESI unit, the heating gas delivery, the ion optics, and we'll also discuss default parameters. In the LCMS 8060 ion focus ESI source, Shimadzu engineers have created electrostatic focusing fields to increase the number of target ions entering the MS inlet. The engineering work for the ion focus system has been going on for some years. Early designs showed that it is possible to improve the ion collection efficiency compared with conventional ESI source configurations, but when the flow rate of the LC mobile phase is high, or when the ESI gas flow rate is high, the increased force of the spray itself tends to make it difficult to improve the efficiency of collecting ions. This design solves that problem. There are essentially 2 electrodes at work here. Number 1, a reflecting electrode positioned behind the spray. On the left-hand diagram, this electrode is charged with voltage labeled V1. The second electrode is a focusing electrode, or lens, positioned in a ring around the MS inlet, and it is charged at voltage V2. V1 is greater than V2, and thus a potential is established between the 2. The strong electrostatic force from the reflecting electrode pushes the electrically charged droplets from the ESI spray orthogonal to the direction of the gas stream and towards the MS inlet. Therefore, the electrically charged droplets, which contain our ions of interest, quickly deviate from the center of the spray. The center of the spray is where the gas stream is particularly strong, and so pushing them off this axis is critical. The focusing lens, seen in the right-hand diagram, acts as a collector for the ions and creates a trajectory toward the MS inlet. The result is that as ions of interest approach the focusing electrode due to the reflecting electric field, the effect of the focusing electric field increases. The ions separated from the gas stream can thus be efficiently collected to an area near the inlet port of the mass spectrometer. In this configuration, even when the spray flow is unusually strong due to high LC flow rates or high gas flow rates, electrically charged droplets and ions of interest can be efficiently introduced into the inlet port. Ions generated in the charged ESI nebulizer are focused into the MS inlet, creating a higher ion density and higher ion sampling efficiency. Neutral molecules are less likely to enter the MS inlet, resulting in less system contamination and greater robustness. In this slide, we see a diagram of the ESI process. The LC effluent passes through a narrow metal capillary, and gas is forced around the nozzle, creating a spray. A high voltage is applied to the vicinity of the needle and induces charged droplets. In this case, a positive high voltage is applied, and the result is positively charged droplets containing our ions of interest. Normally, the ESI spray is positioned in such a way as to maximize sensitivity. However, the spray can be shifted away from the ESI inlet to let less sample into the MS. We recommend this to users frequently. Some labs don't want to dilute their samples. Some labs just don't need the highest sensitivity. So moving the spray away from the inlet definitely reduces the sample load on the MS. And we all know that samples are what gets an MS dirty. In the diagram, you see charged droplets or ions of interest and also neutral molecules. These can be thought of as unwanted matrix or non-volatile material, which is going to adhere to lenses downstream and lead to contamination of the MS. But in the Lcms 8060NX, the ion focus lenses on either side of the spray set up an electrostatic field, preferentially driving ions of interest toward the MS inlet. This is effective even when the spray is moved a considerable distance away from the MS. So the spray can be positioned several millimeters away from the inlet capillary. Unwanted neutral molecules and sample matrix, which lead to contamination, are expelled in the orthogonal spray, but ions of interest are focused towards the mass spectrometer. This results in a high concentration of sample ions, while at the same time, matrix is reduced. The graph on the left shows ion intensity plotted against the distance the spray is positioned away from the MS. In a conventional ESI source, the signal decreases significantly as the spray is moved outwards. This is consistent with our previous discussion. The greater the distance, the less sample is introduced to the MS. Remember, although only the target signal is plotted here on the graph, this reduction includes target ions as well as unwanted matrix. As you can see in a conventional source, with each millimeter of movement away from the heated capillary mass spec inlet, there is a steady drop in signal. If you look at our poster on this topic, WP344 by Hattori and others, you'll see a similar study describing the average signal response for 100 pesticides. These 100 pesticides were spiked into a vegetable matrix and analyzed, first on a conventional ESI source. The average signal for the 100 compounds was calculated at several probe positions. In this study, signal intensity dropped by 86% as the probe and resulting spray were moved farther away from the MS. In contrast, the same analysis conducted on the new 8060NX ESI probe shows that the signal intensity is quite stable, even as the spray is moved further and further from the MS inlet. The NX ion focus system thereby delivers greater robustness to the LCMS analysis. The superior robustness developed by the NX ion focus system is demonstrated here. This graph represents 1,000 repeat injections of a urine sample. After centrifugation, the sample was diluted 1-to-1 in water with no additional cleanup or protein precipitation. The injection volume was quite large, 10 microliters. An endogenous metabolite was monitored for stability of response. As you can see in the graph, there is no loss in sensitivity throughout the analysis, and the relative standard deviation, determined without the benefit of internal standards, was only 8.4%. Again, we welcome you to review Wednesday poster 344, Efficient Introduction of Ionic Compounds into LCMS Using the Improved ESI Unit by Hattori for details. That poster shows photos of the ion source at the conclusion of this study. The exterior surfaces of the ESI source are visibly quite dirty, but because the ion focus system allowed the ESI probe to be positioned at a significant distance away from the MS inlet, the contaminants did not enter the MS. These matrix contaminants were expelled and target ions were preferentially sampled with high sensitivity. Because the matrix contamination was kept out of the MS, the performance was exceptionally stable over 1,000 injections. Another benefit of the LCMS 8060NX system is introduced in this slide. Shimadzu's heated ESI source uses 3 separate gas flows. The nebulizer gas is usually run at only about 2 to 3 liters per minute and is responsible for creating the ESI droplets as the LC flow emerges from the ESI capillary. Another gas, the drying gas, emerges from around the MS inlet and runs parallel but counter to the direction of ion transfer. The drying gas assists in the ESI desolvation process and also helps to reduce background noise. The drying gas is run at anywhere from about 5 to 15 liters per minute. The third gas is the heating gas. Like the nebulizer gas, the heating gas is emitted from around the ESI capillary and flows orthogonally against the MS inlet. The heating gas forms a sheath around the nebulizing gas and assists in the desolvation process. As its name suggests, the heating gas also passes through a heater and delivers thermal energy to the desolvation of the ionized droplets. Shimadzu's heater is placed very close to the ESI capillary so that the heat transfer is quite efficient and yet resists boiling the LC effluent, which would lead to inconsistent spray. Heating gas flow rates are typically set at about 10 liters per minute. In Shimadzu's conventional heated ESI source, the maximum is 20 liters per minute. The LCMS 8060NX ESI source is outfitted with an improved heater and a new gas flow controller capable of delivering higher heating gas flow rates. Wednesday poster 350 by Uno and others discusses the development of an improved 8060NX ESI source, which proved to be beneficial for the desolvation of certain difficult to ionize compounds. In particular, several different steroid hormones from protein-precipitated serum were evaluated for signal improvement under varying temperature and gas flow conditions. First, the relationship between ESI temperature, that is, the set point temperature of the heating gas, and analyte sensitivity was investigated. 12 hormones were evaluated in the temperature range of 200 to 400 degrees C at 3 different heating gas flows. 11 of the 12 hormones studied benefited from both higher temperature and higher gas flows, some more significantly than others. An example of one steroid, dehydroepiandrosterone, DHEA, is shown in the graph here. This data was obtained at an LC flow rate of 0.8 mils per minute. As seen in the graph, more efficient ESI droplet desolvation induced by the heating gas was obtained from the more efficient heating system as well as the capability for higher gas flows. In order to test the new NX heater system more arduously, another investigation was conducted, this time with the LC flow at 1.5 mils per minute. While the DHEA response was found to improve by about 2x at 0.8 mils per minute, DHEA response improved by a factor of 3 at 1.5 mils per minute. This demonstrates that the new NX ESI source, with improved heat transfer and higher gas flow capabilities, can improve ionization of difficult compounds even at high LC flow rates. Better desolvation means better sensitivity, and the new NX heating system produces more efficient desolvation. Another feature of the LCMS 8060NX is improved ion optics. Shimadzu's triple quads use 3 sets of multipole focusing lenses at different vacuum stages of the mass spectrometer. The first is the quadrupole array, or simply Q array, followed by 2 multipole lenses. High frequency voltage is supplied to each of these lenses, inducing convergence of the ions, better ion transmission, and overall higher sensitivity. Shimadzu engineering research combining gas dynamics simulation and ion trajectory simulation has been ongoing. Wada and others in Monday poster 284 discuss some of their findings. Simulation indicated a probable relationship between mass and an ion's capacity to diffuse into the gas, which is present at relatively high pressures in the early stages of a mass spectrometer. Optimizing the ion optics for low mass ions using a higher RF voltage has improved the signal response. The examples shown are monochloroacetic acid and phenol, each of which yielded a signal improvement of about a factor of 2. The result is streamlined ion transmission and a greater system robustness due to a lower deposition rate of contaminants on the lenses. Apart from the hardware changes discussed up to this point, Shimadzu engineers have reevaluated the starting analysis conditions for the LCMS 8060NX. Mass spec operators are aware that optimizing LCMS conditions often requires expertise, rules of thumb, trial and error, or even brute force searching through combinations of interdependent variables. In the case of the LCMS 8060NX ESI source parameters, there are at least 7 important system settings: the interface voltage, nebulizing, drying, and heating gas flow rates, and 3 individual heater settings. Because a full factorial design of 7 parameters is impractical, Shimadzu engineers developed a machine learning process utilizing Bayesian optimization. Bayesian optimization is a machine learning method of parameter optimization with a small number of trials. You can read more details in Wednesday poster 279 by Tagawa and others. The new default parameters of the LCMS 8060NX based on artificial intelligence processes are suitable for a diverse chemical space, enabling excellent results without the need for labor-intensive investigation of analysis conditions. As a result, the art form of mass spectrometer optimization has just become easier with the introduction of the LCMS 8060NX. Out of the box, LCMS 8060NX performance has been improved an average of 2.6 times for a variety of analytes, making the job of method development that much faster. One great benefit of Shimadzu triple quads is our dual ion source. The dual ion source adds APCI capability to Shimadzu's standard ESI hardware. This dual source does not split the flow stream, nor does it alternate voltages. ESI and APCI voltages are simultaneously applied from 2 independent high voltage power supply units, even for methods that use Shimadzu's unmatched 5 millisecond polarity switching. LCMS method development experts know that a high number of analytes in a single method often means compromised conditions, even when the analytes are of the same chemical class. Mass spec voltages can be switched for different MRMs in milliseconds, but gas flows and heated zone temperatures must be held constant throughout the entirety of the analysis. Adding APCI capability to an uncompromised ESI source can be a real advantage in situations like this. The chromatogram here shows a pesticide mix with about 80 compounds. Many of these compounds are specific to various states' regulation of the cannabis industry. Several of the analytes have traditionally been analyzed by GCMS, not merely because of years of laboratory history, but because they simply don't ionize well by LCMS ESI. The chromatogram here includes chlorphenapyr, acequinacil, and MGK264, among others, but their response is good because of the APCI performance of the 8060NX dual-ion source. The 8060NX default conditions show a marked improvement in signal over previously optimized LCMS 8060 conditions. Superior out-of-the-box performance is demonstrated here as ion-focused technology, new optics, improved heat transfer in the source, and intelligent default conditions combine to improve signal-to-noise and detection limits for difficult-to-ionize compounds. Since the release of the new Nexera UHPLC series, analytical intelligence has been Shimadzu's theme. Analytical intelligence uses automated support functions to deliver unattended operation and recovery from common errors. Nexera can be set to start up at a specified time so that it can complete auto-purge, equilibration, and baseline checks in advance, and be ready for analysis as soon as you arrive at the lab. The system can be set up in advance to run without user intervention, all the way from startup through analysis to shutdown. Nexera autosamplers and pumps are rugged and precise. Pumps deliver mobile phase for every style of analytical column with minimal pulsation, and retention times are rock solid. Nexera autosamplers have high capacity, are fast, clean, and reproducible even at injection volumes below 1 microliter. And they also provide advanced, programmable micro-volume liquid handling capabilities. The Nexera 40 series lineup has UHPLC and HPLC systems appropriate for every lab. The Nexera 40 series is highly configurable with multiple pressure rating options up to 19,000 psi. Nexera sets the standard for LCMS sample delivery. One example of analytical intelligence is Nexera's Flow Pilot. HPLC columns can be damaged by sudden pump starts and stops or extreme gradient changes. The Nexera automatically uses Flow Pilot to increase the flow rate gradually to a set point based on column oven temperature. There is no need to create startup protocols for each analysis. Nexera systems can also monitor mobile phase levels in real time and auto-diagnose an air bubble in a pump's check valve. When an unusual pressure fluctuation is detected, the system can automatically pause the analysis, purge the flow path, and restart the analysis once it has confirmed recovery to normal pressure. Shimadzu's analytical intelligence is also represented in the control of the mass spectrometer. MRM optimization has always been easy in Lab Solutions software. No syringe pump is needed, only a few 30-second flow injection runs via the autosampler. A simple graphical user interface allows the operator to check a few radio buttons, load the autosampler with standards, and queue up a batch to automatically optimize analyte after analyte. Only a few MRM voltages require optimization, and each takes only 30 seconds or less. For example, the MRM wizard runs full product 9 spectra at 9 different collision energies, automatically selecting the most intense product 9 candidates from their respective optimal collision energies in a single injection. Now, with Lab Solutions Connect software, reviewing the results is easier than ever. Product ion spectra, collision energy data, and MRM chromatograms are all shown on a single review screen for rapid confirmation of optimal voltage selections. As discussed earlier, ESI source parameters are among the most difficult to optimize, not only because they are interdependent variables, but because the latency of heated zone and gas flow stabilization makes the process time-consuming. When interface optimization is desired, Connect software enables one factor at a time automated optimization. On column or using flow injection analysis, the Connect algorithm orders the testing of the various source parameters in a sequence prescribed by years of method development experience. If the default order is used, parameters fundamental to a wide variety of molecules are tested first, and all subsequent tests automatically begin with the previous optimal values. The screen capture here shows the results of the Connect interface optimization experiment. The interface voltage and collision gas pressure were followed by gas flow optimization and finally temperature optimization. All the results are shown in a single, easy-to-review graphical format. In 2016, Shimadzu began research using artificial intelligence in collaboration with Fujitsu Limited and Fujitsu Laboratories, each company bringing its own expertise in mass spectrometry techniques, equipment knowledge, and AI-based deep learning know-how. The goal was to create an AI program to automate the process of peak detection. In order to do this, the partners needed to find ways to generate training data for the system to learn on and to be able to convert chromatographic waveform data into images that the system could read. A number of approaches were tried, with each team offering suggestions during discussions on requirements. Finally, in June 2017, ideas to resolve the problem began to take shape. The Fujitsu teams found that converting the numerical values of measurement results into images and using the data to examine waveform contours were effective ways to achieve the specified accuracy. Meanwhile, the Shimadzu team developed technologies to automatically generate the training data needed to enhance the effectiveness of deep learning. After applying deep learning to more than 30,000 images, they succeeded in increasing the accuracy of peak detection. As of November 2017, the program was advanced to a point where work requiring about 2 hours of experienced operator time was achieved in just several seconds. However, compared with manual peak picking results by an operator with more than 10 years of experience, the automated peak detection results using AI had a false detection rate of 7% and an undetected rate of 9%. Work continued. By incorporating deep learning into the dedicated analytical software, the team succeeded in automatically identifying peak identification with the same accuracy as experienced operators. Also, they managed to smooth out analytical precision discrepancies that occurred with different operators. The end result is a peak integration algorithm that requires no threshold, no slope, no peak width or baseline settings. Thanks, everyone, for attending the presentation so far. We're now going to turn from the new NX triple quad and look at advancements in Shimadzu's high-resolution platform. The LCMS 9030 is Shimadzu's high-resolution accurate mass Qtos. Built on the high-sensitivity LCMS 8060 triple quad platform, the 9030 Qtos delivers exceptionally stable mass accuracy because of its meticulously controlled flight tube temperature system, as well as high-sensitivity detection due to its ion accumulation electronics. Software capabilities have been expanded, and they're being shown for the first time here at ASMS 2020. At ASMS 2020, we have launched new software capabilities to get better data and make faster decisions. Using the high sensitivity of the LCMS 9030 and the simplicity of its rugged, robust operation, a platform has been designed for routine, high-resolution, accurate mass assays for targeted workflows. In this example, we are showing a plasma sample processed by a simple protein crash and a catcher's extraction. A positive library verification and high mass accuracy ion ratio confirmation is seen for the target compound fentanyl as compared to a 10 nanogram per mil calibration standard. A generic MS and DIA MSMS method was used to acquire all the data using external mass calibration only. Note also that all this data was processed using peak intelligence. This is a platform that can be placed in any routine application in any lab to deliver the confidence you need in making the right decisions. Library searching and identification are core tools in high-resolution accurate mass data analysis. As part of the drive to make assays scalable and add value to the decision-making process, we have made a change to building libraries. The new library editor is a powerful, flexible workspace to create new libraries easily. You can import compound metadata from a database or spreadsheet. Corresponding MSMS spectra can be added from your Qtos raw data that was acquired in DDA or DIA mode. DIA deconvolution is supported. MSMS spectral data can even be imported into the library from an external database. You can edit the product spectrum to display fragment annotation and theoretical accurate mass for easier library verification. It makes a step change in building new HRAM MSMS libraries. Lab Solutions Insight now has a streamlined suspect screening workflow. With a duty cycle of less than 1 second, acquisition of MS and DIA MSMS data in a single injection allows for in-depth targeted analysis while reducing the potential for false negatives. Step is feature detection in the MS1 total ion chromogram. Insight uses the Analytes engine to examine thousands of adjacent accurate mass spectra to find repetitive patterns for individual masses. These pattern results are examined for Gaussian or peak-like behavior. The results are filtered, and the detected accurate mass features are displayed in the results table. Because of the richness of high-resolution accurate mass data, it is typical to find 1, 2, or even 3,000 individual features or peaks in a single sample. If just accurate mass information is used, the risk of false positives becomes high. Therefore, a user-prepared targeted suspect list is compared against the feature detection results. A targeted list reduces the number of false positives likely to be found. Comparison against the target list by mass, or MZ, isotopic ratio, and retention time further reduces the number of false positives. Data review proceeds as formula prediction results are generated and displayed for the suspect target hits. The review table is automatically arranged to compare target and predicted formula, ppm difference, and scores. Library spectra can then be easily viewed and compared to the deconvoluted DIA spectra for final confirmation. Sign can be used to help accelerate unknown identification and compound verification workflows because a sign delivers a powerful product ion fragmentation analysis tool. Starting with an electronic molecular structure, or mole file, or the results of a ChemSpider or PubChem search, a sign uses a sophisticated cleavage algorithm to compare your experimental MSMS data with theoretical fragmentation products. A sign then structurally annotates product ion spectra with each candidate structure. If the fragment ions can be structurally verified with the candidate structure, it is considered a possible true hit. A scoring system based upon the number of fragment ions identified can be a helpful tool to filter possible structures. In the example shown here, a suspect hit for fentanyl was observed. The suspect precursor mass was used to initiate a ChemSpider search. A precursor formula can also be used for a database search. The DIA acquired product ion spectrum from the raw data is displayed in a sign, as well as matching fragment ion identifications. Well, that concludes our presentation for this afternoon. Thank you for attending our talk at ASMS 2020. I'm sincerely hoping that we can all meet face-to-face next year and do more than an online format. We're going to move to our Q&A session now. If your question does not get answered in the Q&A session, we will be reaching out to you via email to try and answer your question the best we can. Thanks again for attending. And moving on to the Q&A, we'll take a moment to satisfy our legal department.
Thank you, Chris, for that excellent presentation. While it would have been great to be on site in Houston to have the LCMS 8060NX highlighted in our suite for everyone to see in person, your presentation provided a great overview of the new technology. Thank you as well to our audience for spending time with us this afternoon. If you hadn't had a chance yet, please take a moment to complete the survey or visit some of the resources. We will now go ahead and answer some of the questions that were presented to us during the presentation. First off, Chris, if you're ready, we'll go with what kind of ionization modes are available in the LCMS 8060NX?
Okay, sure. Basically, the ESI source for the NX is standard. That comes with every unit. But you can also purchase APCI and DUIS sources. DUIS source is the dual ion source that I mentioned in the talk.
Okay, great. The next question, in slide 4, you mentioned that the new source design can help to get rid of contaminants. How do you define contaminants in this case?
Well, yeah, it's a good question. Contaminants, in this case, are neutral molecules and non-volatile and semi-volatile material. This is the kind of material that we understand adheres to the inner components of the mass spectrometer, the lenses, the support material on the lenses, things like that. So this is the kind of matrix and unwanted material that is not put into the mass spectrometer in the NX model.
Okay, great. This next question comes from a bioanalytical chemist. This person encounters challenges developing and validating methods when dealing with complex tissue matrices. Is there any preliminary data on how the 8060NX will help in decreasing matrix-related signal suppression?
Wow, that's an excellent question. I alluded to some data that we had during the talk. Basically, this is data where we had 100 pesticides and we spiked them into a vegetable matrix. We measured the matrix effect by recovery. So the spiked recoveries were the indication that the matrix effect had been minimized. And if you remember that slide, when we moved the probe outward on the standard 8060 model, the matrix effect was, in fact, reduced. But in the NX source, we were able to maintain strong signal even when the probe was moved outward, and we were also able to reduce that matrix effect as measured by the recoveries. So there's more data on that in Wednesday poster 344 if you care to look at that.
Okay, great. Okay, Chris, the next question. Is there a change in detector as well for the NX, or is it mainly the front end of the instrument?
Well, no, the changes are to the front end of the instrument. The detector is the same pulse counter and electron multiplier that's in the standard 8060 model. So the changes to the NX are in the front end and also in the overall default parameters which are applied to the instrument. Okay,
that sounds good. Next question is, does the better ion focus and ion optics imply lesser need to work on sample preparation steps, such as SPE or LLE?
Well, that's a good question. I think our urine data that was presented during the talk demonstrates this. So that sample was intentionally prepared with no SPE, not even any protein precipitation, and just a simple dilution 1-to-1 with water. So we considered that a very good test matrix for this, and it performed very well over 1,000 samples. So we think that the instrument will stand up to quite dirty samples.
Okay. This next question relates to sensitivity. How far can you set the probe without affecting sensitivity on the new model? Is there any effect on sensitivity due to moving the probe away from the MS inlet?
Okay, great question. Yeah, on one of the slides there, we had that graph showing the ion intensity as it relates to probe position. Now that graph documented the probe position all the way out to 5 millimeters. And even at 5 millimeters, there was no decrease in sensitivity with the NX system. So we think this is a very important capability of the instrument to be able to maintain that high sensitivity while most of the sample is basically going out in the spray and down the drain.
Okay, sounds good. Next question relates to the software, the Lab Solutions Connect. Which source parameters are being optimized by this software? Do I need to obtain separate licenses for it?
Oh goodness, yeah. There's 7 parameters that we enumerated in the talk. Basically, let's see. It was interface voltage, 3 gas flow rates: the heating gas, the drying gas, and the nebulizing gas, and then 3 individual temperature settings: the temperature setting for the heating gas, the temperature setting for our desolvation line, and our heating block, which is a component that surrounds the orifice of the inlet to the mass spec. And yes, you do need to purchase a separate license for Connect. Very reasonable price on that, but it is not included with every system.
Okay, good to know. Now we have, can you briefly explain how does a typical workflow look like for unknown identification on Qtos?
Okay, so I take it that this question is in reference to an unknown or unknown as opposed to a targeted unknown. So basically, you'll obtain accurate mass data from the Qtos for the unknown peak, and then based on the accurate mass data, we use our Lab Solutions Insight software to generate a list of possible formulas and comparing isotopic patterns. So basically, you'll get a score and a ranking, and usually we get the highest hit is the right answer, usually. And at that point, you can then do a call to a database such as PubChem or ChemSpider, and you can perform MSMS fragmentation comparison against these databases. True unknowns that aren't present in the database, that still requires a good deal of chemistry knowledge, but that's basically the workflow.
Okay, that sounds good. So this new model, the 8060NX, includes a new pusher and puller electrode design. Do the other Shimatsu LCMS models include this?
No, this is a new feature, and it's only been incorporated into the LCMS 8060NX, and currently that is the only model that has this new ion focus design.
Okay. Our next question, if a greater number or neutral molecules is deterred from the MS, does this imply less instrument maintenance, and does this extend the time between needed instrument PMs?
Absolutely. This is what we've seen in our product development, and this is what we expect to occur in customer laboratories as well. The ion focus unit keeps the contamination out, and the new optics minimize deposition, and so we definitely expect longer maintenance intervals on the NX series.
Okay, great. Okay, Chris, the next question is, what is the polarity switching time available on the new 8060NX? And can I run one method with analytes in both positive and negative modes?
Absolutely. The polarity switching time is maintained from the previous series, so that's 5 milliseconds, and our polarity switching actually works.
Okay, well, that's an easy question and answer. The next question would be, does Shimatsu have a software to process the DIA and DDA data on the Qtos?
Yes, our newest version of Lab Solutions Insight, which basically is being released here at ASMS 2020, is capable of processing both DIA and DDA data in one workspace. So you can obtain precursor ion information, look at fragment ions, build and conduct library searches, and a lot of other capabilities. DIA deconvolution is also possible.
Okay, and this is somewhat of a follow-up question. Can you use library search, the library search feature on DIA and DDA data?
Yes, you can. It does support that.
Okay, and is it recommended that the library be developed in the matrix?
Wow, that's a pretty complex question. There's a lot of nuance there. Personally, I think it is better to develop libraries in a compatible matrix or comparable matrix. If you think about taking a spectrum from an unknown sample acquisition, you might have a number of background ions in there that would not be present in the library spectrum. Not that we expect those ions to match up necessarily, and the library spectrum is really going to be compared for the values that are present. But I think it'd probably be a good idea to do it that way. That's a difficult question.
Okay. All right. Thank you. Our next question is, can Qtos data be transferred into a third-party compatible format?
Yeah, absolutely. We can output raw data into MZML, MZXML, which can be read by most any third-party software.
Okay, sounds great. Next, do I need to run my samples with an internal standard or a lock mass standard to ensure the mass accuracy stays high when I perform suspect screening search?
No, definitely not. Our Qtos has mass accuracy of 1 ppm, and because of the temperature control system, that is extremely stable. And so we never use a lock mass. The software does allow you to use external mass calibration from a tune file. We usually do that every few days. You can actually run data in your batch and use those, run standards in your batch and use those standards to interpolate the samples in between those standards if you want to refine it. But frankly, we never do that in our laboratory because we just don't need to. So external standard only with our tune file is the way we approach that.
All right, sounds great. All right, our next question is, will I be able to use MSMS spectra obtained from another vendor's Qtos in my library?
Yeah, we can definitely import the MSMS spectra as a text file into our library. So you can go to an external database for that. The ion ratios might be a little bit different because you've got different hardware there. Also, the collision energy is a very interesting component to consider. Frequently, when we're doing DIA data, we're going to be using a collision energy range around a typical voltage. So depending on what voltage or what voltage range was used in the database library acquisition, you might see some differences in ion ratio.
Okay. All right. This next question is really like a two-part question. After using the enhanced MRM and interface automation functions, will the software present the best method where I can start running the samples? Secondly, will I have to go through each data file to look for the best conditions?
Okay. Yeah. Basically, I think it's really the same question, and absolutely, the MRM automation software will go through all the functions that you need, and it will write that directly to a method file that you can utilize. It will also create individual method files for individual analytes that you can kind of mix and match later on. But when you review the data, it's all right there in one screen, so quite easy to do.
Okay, great. Next, we have how often do you need to tune the Lcms 9030 Qtos?
Well, that's very similar to what I was alluding to a few minutes ago. The TOF calibration, we do that every few days, and that only takes a couple of minutes. The full tune on the instrument, which includes the quadrupole tuning, that we only do every few months. So I hope that clarifies.
Okay. And next, is peak intelligence included in Shimatsu's LCMS software?
Good question. No, it is not included by default. Peak intelligence is distributed by Shimadzu under license from Fujitsu, and so it's available for purchase. Okay,
good to know. And next we have, does enhanced MRM automation find the true molecular weights, or do users need to input this information?
Okay, that's a good question. There is a function in the MRM automation tool which will experimentally determine the precursor and product ion masses. we always recommend that that the customer use a theoretical precursor ion mass and then use the measured product ion mass. We think that produces the more robust method for work for a long period of time, and also for dissemination to other instruments of the same platform.
All right, that sounds great. And you know, and Chris, I think at this point, I think we've used up enough time for many of our attendees, many of whom I'm sure are attending other events or looking at posters with the ASMS 2020 reboot. So I think we'll do it and end the session now. I want to thank Chris, and then thank all the attendees rather, for all the interesting questions. We may not have gotten to all of them, but rest assured we will respond individually to any questions that we weren't able to answer now. Once again, thank you, everyone. Following the webinar, you will receive an email with a link to view a recorded version of the presentation at any time. So if there's anything you want to go back and forth with, you'll be able to do that then. So for now, thanks everyone again. Have a great day and enjoy the ASMS 2020 reboot.
Thanks, Kevin. Much appreciated.